Okay, so page 2, we are going to build on our understanding of end behavior of polynomials and apply those same rules to end behavior of rational functions. Because just because we throw in a fraction to now make a variable on the top and the bottom, it still abides by the same principles that if it just didn't have a denominator in the first place and it was just some regular polynomial. So when we talk about end behavior, we know that we're talking about very, very large positive numbers to the right, plugging in for x, and very, very large negative values to the left. So we're trying to figure out what's going on at the ends instead of what's in the middle. So with polynomials, as we know, we determine this end behavior by focusing on the leading term, because ultimately, when the numbers get really big, that's the only term that's going to matter. Good news is about rational functions, we're still going to consider the leading term. We just need to make sure we're considering both the numerator and denominator. So we're going to do a little bit of reducing here with these three functions to try to figure out, hey, what is my end behavior going to look like? So the rational function below, we're going to circle, highlight, denote the leading term, just focus on those two, simplify, and then see what we're talking about. So because we should always be keeping up with the stuff we've learned before, make sure this is clear. We know that there's a vertical asymptote at x equals -1 because that's where our denominator would be equals 0. Okay, so we're focusing on the leading term, which is 2x to the 4th. So I'm going to write that on the top and then x. So each top and bottom of the fraction, we're going to focus on the leading term for that. Now, let's reduce here. So we have 2x to the 4th divided by x. We're going to keep our 2. X to the power of 4 divided by x to the power of 1. We're going to reduce that by 1 degree, so we're going to have 2x to the 3rd. So now we've simplified our leading terms. So now we look at this, and this is where we use our end behavior idea of polynomials. So we have a positive leading coefficient, which automatically means that our right side is finishing up. And we have an odd degree, which means that our left side will be finishing down. So there's a lot that can go on in the middle. There's a lot that's going on in the middle, but our function is ultimately going to go up and positive to the right, and it's going to go down and negative to the left. Let me fix that arrow there. Because it behaves the same way as though we were just looking at a polynomial where we focus on two things, leading coefficient and degree. Okay, so let's look at a of x here. So same thing, we just want to kind of keep our skills on the up and up. We could factor the denominator to be x plus 2, x minus 2. So that means we're going to have vertical asymptote at positive 2 and at negative 2. Because 2 squared is 4, 4 minus 4 makes 0. Negative 2 squared is 4, 4 minus 4 also makes 0. Okay, but when it comes to end behavior, so we're going to focus on the leading term here, so negative 3x squared, and we're going to focus on the leading term in the denominator, which is x squared. So the x squareds cancel, and all that we're left with is a negative 3. So since there is no degree, because negative 3 is a constant, and it doesn't have degree, and since it's its own number, it's just a leading coefficient, this is where we end up. This will have a horizontal asymptote at that value. So this will have a horizontal asymptote at y equals negative 3. And what that will look like is the function will ultimately end up flatlining at that negative 3. So instead of going up or down, as we've previously seen with end behavior, it will flatten out at that whatever constant value, in this case, negative 3. Okay, so if the last case that we have yet to consider, so if you kind of look here, and we'll get to this on the next page, but notice in r of x, the degree in the numerator was larger, x to the 4th compared to x to the 1st. In this one, a of x, the degree is the same, x squared in the numerator compared to x squared in the denominator. So the last case we want to consider is, well, what if the numerator is smaller than the denominator? So in b of x, we're going to focus on x squared as our leading term in the top and x cubed as our leading term in the bottom. Two of these x's are going to cancel, which just leaves a 1. And 2 of these x's are going to cancel, but it still has the 1 left over, which is 1 over x. So now we're thinking, okay, well, where is this end behavior going to be? Well, it's not a polynomial because polynomials can't have x in their denominator. So we can't really focus on a leading coefficient or degree. But let's focus on the idea of, well, what if we started to plug in larger and larger x values? So let's think about this. Start with 10, then go to 100, then go to 1,000, then go to 10,000. So as you plug in values for x, your asymptote starts at 1/10th, then it goes to 1/100th, then it goes to 1/1000th, then it goes to 1/10,000th. And what we should be seeing is that as we move this way, we are essentially getting closer and closer to 0, because once we get to something like 1/1,000,000th, it's essentially going to be 0. So anytime now that you have something that's a constant in the numerator and you have something that's changing in the denominator, well, as that thing changes, it's going to get closer and closer to 0 because you're dividing 1 by bigger and bigger and bigger numbers. So this is where we're going to have a horizontal asymptote at y equals 0. So we're going to flatline since we have that horizontal asymptote. To the left and to the right, we're going to flatline at y equals 0.